Okay, we are going to start this chapter 2, so derivatives, and we're talking about vectors. So this is the typical picture of a function. We talked about this already, but we have a function which takes elements, inputs, and gives you outputs. And 2 is the codomain. And the function is often spoken of as a rule, or a way of tells you which this element goes to where. So that's the rule. And here we have the notation that says that it takes elements from set X and outputs elements from set Y, or points to elements in set Y. So we can say like a social security number is a function which goes from the set of US citizens to a bunch of numbers. So X doesn't have to be a numerical set, although for us it usually will. However, in this example, the set of US citizens is the domain. Another example is assigning dorm rooms to students. So then you would have students and dorm rooms as the two sets of students and sets of dorm rooms. And the concept of the range, I guess, I think the codomain is the set of all possible, I always get this confused, but the set of all possible values, and then the range is here, the set of y in y, such that f of x equals y for some x. So the range has to have, so you might have a whole lot of y's here, but only some of them get actually hit by values from the domain. So the ones that actually get hit are called the range. And that's what this definition says. Okay, we also have a word called onto, or surjective. So if that means if every element in Y is the image of some element of X, that is, if the range of F equals all of Y, it means every element in Y gets hit by something. So they say the social security function is not onto, since this is in the codomain but not in the range. So nobody, I guess, has this number. Okay, then we have a concept called one-to-one, or injective, and that means that this doesn't happen. What I mean is, here we have this element going to here, and we also have this element going to here. So that means they're both going to the same Y element, and that's not one-to-one, or that's not injective. So they say a function is called one-to-one if no two distinct elements of the domain, so two distinct elements here of the domain, have the same image. We say this is the image of this. We say this is the image of this. So if no two distinct elements of the domain here and here go to the same element in the range, then it's called one-to-one. So this is not one-to-one because we have two distinct elements going to the same one. And more formally we say that is f is one-to-one if whenever x1 and x2 are in the here and they are not equal, then f of x1 cannot be equal to f of x2. If that's true, then this is called one-to-one, or an injective function, or one-to-one function. So again, this is one-to-one, but this is not, because there are two going to the same one. Okay, let's take a simple example. X squared, the domain and the codomain are all of R, so we say that it's all of R and all of R, but the range, so the codomain is all of R because that's what they said it was, but actually there's no Y values that are negative. You never get a negative value from this, so nothing, the outputs are never negative. So the range is only 0 to infinity, so it's only non-negative. So f is not onto because we specified that now I get confused, that the codomain is R, but the range is not all of R. So not all of the codomain gets hit. Okay, also note that f is not 1 to 1. For example, both, if you put in 2 and negative 2, that's in the domain, right? You can have negative numbers in the domain. You can't have them in the range. Or yeah, you can have them in the range. But anyway, if you put 2 and negative 2, they both get mapped to 4. So, but 2 and negative 2 are not the same. So we have two different elements in the domain going to the same element in the codomain. Okay, and here's another one. You can read this. Okay, now we're ready to think of functions of more than one real variable. So we can talk about functions from that are vectors. So in an n-dimensional vector or an n-dimensional space, and getting mapped to vectors. We said in class that when this is more than just R, so if it's R2 or R3 or anything, then we capitalize this when this one is more than just R. Okay, so here is a function called t, which goes from R3 to R. So it's a scalar valued function, as we said. So it takes 3 values as input, so we can say the elements are from R3. The input is from R3, but the output is just a scalar, just this stuff. So they say we can think maybe a temperature function. So x, y, z is the coordinates of a point in R3. So it's the coordinates in space. And then this gives us, depending on the coordinates, we get a certain temperature out according to this formula. So for example, at 0, 0, 0, it's 0 plus 0 plus 0, but at 0, 0, 1, it's 0 plus, no, that's still 0, and that's still 0, so it's still 0. At, let's say, 0, 1, 1, so this is 0, this is 0, but this is 1. So it would be maybe 1 degree at that location. Okay, here's another example. That was called t. Notice it's not capitalized because this is not more than R1. This is called L. This is also not capitalized. So L takes a vector from Rn and gives us the magnitude of that vector, which is just a scalar. So this is a length function in that it computes the length of any vector in Rn. And then they say, note that L is not 1 to 1. For example, these two, remember this means one of the basis vectors, and this is a different basis vector, but L will take both of them to 1, even when they're obviously not the same basis vectors for any two standard basis vectors. L also fails to be onto rather. The length of a vector is always non-negative, so so negative values are not being hit. Okay, now suppose we have a vector as an input, but notice this is bold, so the output must be a vector, not just a scalar, according to what I said about the notation. So what is that true here? So we're doing this. Remember, this gives us, this normalizes, this creates a unit vector, or it's also called normalizing the vector. So this creates a unit vector. So you can see that we're dividing by a length, but that's that doesn't change. So this is a vector divided by a length. It's still a vector. So this input's a vector and output's a vector. So therefore, this should this is bold. Okay. So they're saying suppose x is a vector in R3. Note that n is not defined at 0. Okay, so n is not defined at 0 because you can't do that. So the largest possible domain for n is R3 minus the point 0. Can't have 0 in there. The range of n consists of all unit vectors in R3. All unit vectors in R3. The function n is the normalization function, that is the function that takes a non-zero vector in R3 and returns the unit vector that points in the same direction. Okay, they also say that sometimes a function isn't necessarily given by a formula, it could just be given by a table. So this is wind chill. So if the temperature is actually 40 degrees, they're talking about Fahrenheit, but anyway, if the temperature is actually 40 degrees, but if it's cold, if it's windy, it'll feel colder. So if it's 5 miles per hour wind, it'll feel like 36. If it's 30 miles per hour wind, it'll feel like 28. So this is not given necessarily by a formula, just this table describes the function. So the input is the actual temperature, and the output is these numbers here, which is what it feels like. I'm sorry, no, wrong, sorry. This is, this is a vector input and a scalar output. So the input is this, comma, this, so it's a vector, or this, comma, this. And the output is this, for example. So it's input is a vector, but the output is a scalar. Okay, here's an example of a scalar input, but we get a vector output. So here we get a vector output. You can see that it's a vector output just by identifying that there are commas here. So that means, if I can get this, that means that the output is a vector. This is a vector. So you're given a t, you get this. The graph of this looks like this. So we're looking at the output. Now this is a parametric equation. In parametric equations, we almost never graph the t. The t is like time, and it's not graphed usually. And all we're looking at is the output as t increases. So as t increases, these two make it kind of go in a circle. But this one is the z variable is always increasing. So it's like a circle, but it keeps going up. So it looks like, they call it a helix or a corkscrew. Okay, here's another example talking about the velocity of a fluid. So we can think about a river or any kind of fluid. Of course, we need to specify the location. Of course, we need to specify a point in R3, but we're also going to be including the time. So we're going to be giving the velocity of at a specific place and at a specific time. So we're going to allow for the velocity to change over time, even at a particular point. So this is a vector input, and it's R4. So we say that the domain is a subset of R4, and the range is going to be the velocity, and velocity can point basically in any physical direction, in any direction basically. So it can be anything in R3 can be the velocity. So we need the I component of the velocity, the j component, and the k component. So this is a vector, this is a function, a vector valued function, velocity, from R4 to R3. And this could be an example. Here's a picture, another picture. So at any particular place you have, and any particular time, you have a velocity. And a velocity points in a particular direction, and it also has like a magnitude. And it's given by this. Given this input, we get this output, which tells us the velocity. Okay, now we're going to call this part the ith component of the output. And we're going to call this part the jth component of the output. And we're going to call this part the kth component of the output. And you can see that each one of these is a function. This is a function, this is a function, and this is a function. And also, instead of calling it the ith component, because we don't always necessarily mean just 3 dimensions, like here we have just I, j, and k, but of course we want to allow for functions beyond just R3 as the output. So maybe we shouldn't call this the ith component, we'll just call it the first component, and we'll call this the second component of the output, and this we'll call the third component, and so on. And each of these is just a function. Is a function, and each one is a scalar valued function. So this just gives you a scalar, right? When you put in x, y, z, and t, you just get a scalar out for just this part. Not the I, just this part here. And this just gives you a scalar output. If you put in x, y, z, and t, in this case you don't need z and t, but x and y, and that will give you a scalar. So this is called the first component function, this is called the second component function, and this is called the third component function. So the component functions are the scalar functions that give us the outputs. So we can say that if f goes from Rn to Rm, and then you see the bold F, so that means that it's vector valued, and that means that m is not 1. So we can think of it in terms of the component functions. So the f1 is called the first component function, and that's here. And f2 is the second one, and that's here. So we have these f1, f2, fm. If the codomain is Rm, then we're going to have m components, and so here we denote them like that. The component functions are scalar valued, and they're scalar valued functions of x, the bold x. So in this case, x, not necessarily, right? We saw that they don't actually have to have all, well, let's say, anyway, they're elements of here, although they may not have all of the x's. We saw this one only has x and y, it doesn't have z and t. Okay? So, so what we get is, so what's going on here? So this is the situation. We have a vector valued function, bold f, with vector input. These represent the inputs, and the output is a vector. So we could write x, y, z, t, comma, this, comma, this, right? That means a vector, the commas, but we're calling them f1, f2, and fm, right? And they take vectors as inputs, right? This is a vector. This needs a vector to give us x, y, z, t. Okay, so we can write it like this, Or we can even write it like this, where we write out all the elements of the input here, and this is the first component function. Okay, so this is kind of messy, as she says, a morass of symbols, but we could write it out like that. Okay, for example, this function was the length function. Now, its output is just r, so it's not such a great example, I think, because there's only going to be one component function. In fact, no. I guess you can call it a component function, but it seems like it should be multiplying a vector, and we don't even have a vector of any sort. That seems a little strange to use as an example, actually. But, for example, this function, when expanded, becomes this. She doesn't say that those are the component functions. Or, I mean, that this is the component function. Anyway, this seems like a bad example. But let's try this one. So this was start with x and get a unit vector in the same direction as x. We did this part. We did this already. And basically, x is now expanded like that. And then the norm of x is written like this. So we get that, which can also, of course, be written. This means that you divide each component by this. So that's what they did here. They divided each component by that. So the component functions are this one, and this one. So this would be called f1, this would be called f2, and this would be called f3. Or actually they're calling them n1, n2, and n3. Okay, so we sort of explained that, but then she says, although writing a function in terms of all its variables and components has the advantage of being explicit, quite a lot of paper and ink are used in the process. The use of, so now she's saying that vectors kind of like simplify everything. So if you saw this, it's sort of crazy and confusing, maybe more than this. Maybe, right? But anyway, both are true. This is one way. This is another way to write it. The use of vector notation not only saves space in trees, but also helps to make the meaning of the function clear by emphasizing that a function maps points in Rn to points in Rm. Vector notation makes functions of 300 variables look like a function of one variable. To try to avoid writing out components as much as you can, except, okay, so next we're going to talk about visualizing functions. This is an example of visualizing a simple function, just a function. Now I mix up. Sometimes I'll say this is a function of in one dimension or two dimensions. So I don't know which is the right way to say it necessarily, but you could say it's in R2. It's not in R2, but this plane is R2, but the output is just R1, right? This is just R to R. So you could say either way. But anyway, so that's what we think of when we think of visualizing a function. However, here we have a function from R2 to R, which means a function of xy that goes to a scalar output, and here it is. And the way you have to visualize that is you'd say down here is the xy point, the input, and the height is the output. So at different xy's you get a different output, you get a different height. So this is the surface, this is a surface that indicates the output. So we're going to come back to this in a second. Anyway, we're going to learn about what are called level curves, which is, you basically are already familiar with level curves because or something basically the same thing as level curves, like when you look at a map and you get these contours, a contour map. Do they have any pictures? This is a kind of contour map of this. So anyway, if you look at a map of an area, sometimes they'll do that, and those will indicate the different heights. Okay,